Hello everyone, welcome to Power Electronics. In this session, I will be discussing the steady state characteristics of the bipolar junctional transistor. In one of my previous sessions, I had discussed the three possible configurations of a BJT. Although there are three possible configurations, the common emitter configuration, as we have shown in figure 1a here, is generally used in switching applications. The typical input characteristics of base current IB against the base emitter voltage VBE is shown in figure B here. Also, figure C shows the typical output characteristics of collector current IC against the collector emitter voltage VCE. For a PNP transistor, the polarities of all the currents and voltages will simply be reversed. Looking into the output characteristic curves of this BJT, we find there are three operating points. The first one is the cutoff region, the second one is the active region, and the last one is the saturation region. Now I will discuss each one of them. Starting with the cutoff region. In the cutoff region, the transistor is off or the base current is not enough to turn it on and both junctions are reverse biased. In this region, BJT offers large resistance to the flow of current, hence it is equivalent to an open circuit. Now in the figure C, what you are looking at, the shaded portion of the graph below the IB equals to 0 curve is what is the cutoff region. Coming to the active region now, in the active region, the transistor acts as an amplifier where the collector current is amplified by a gain and the collector to emitter voltage decreases with the base current. The collector to base junction is reverse biased and the base to emitter junction is forward biased. The collector current IC increases slightly with an increase in the voltage across the collector to emitter terminal if the base current is increased. The relation of IB and IC, that is IC equal to beta IB, is true particularly in the active region. If BJT uses as an amplifier or as a series pass transistor in the voltage regulator, it operates in this region. The dynamic resistance in this region is large. Also, the power dissipation is maximum. Lastly, coming to the saturation region can be further divided into two regions, quasi-saturation region and hard saturation region. And in order to discuss these regions, I am going to use another diagram as you can see here. Right, so this is what is the portion across the saturation. We have divided the saturation region graph into two. This line what you are looking at, this is the hard saturation point, and between this line and this line what you are looking at is the quasi saturation region. Let us discuss what are these regions. Quasi saturation region is between the hard saturation and the active region. This region exists due to the lightly doped drift layer. When the BJT operates at high frequency, it is operated in this region. Both junctions are forward biased. The device offers low resistance compared to the active region, so power loss is less. In this region, the device does not go into deep saturation, so it can quickly turn off. Therefore, we can use this region for higher frequency applications. Now lastly, coming to the hard saturation, the power BJT push into the hard saturation region from the quasi-saturation region by increasing the base current. This region is also known as deep saturation region. The resistance offered in this region is minimum. It is even less than the quasi-saturation region. So, when the BJT operates in this region, power dissipation is minimum. The device acts as a closed switch when it operates in this region, but it needs more time to turn off. So this region is suitable only for low frequency switching applications. In this region, both junctions are once again forward biased. The collector current is not proportional to the base current in this region, and the collector current remains almost constant at the value of ICS, the collector saturation current, and is independent from the value of base current. Right, so that was about the input and output characteristics of the BJT. Now we will continue to the transfer characteristics, which is a plot of collector to emitter voltage against the base current, as we are looking at the figure 3a here. The model of the NPN transistor is also given in figure B, which is under the large signal DC operation. In this particular approach, we see that, particularly talking about the transfer characteristic, the x-axis is the base current, the y-axis is the collector to emitter voltage. As the base current increases slowly, the collector to emitter voltage starts to drop, and when the base current is very small, the collector to emitter voltage is almost constant, in which case we say the device does not respond and therefore it is in the cutoff region. Now, in the active region, the slope of the curve is pretty large, and therefore in this particular region we say the BJT acts as an amplifier. Lastly, coming to the saturation region, when the base current is increased, you can look at this, the collector to emitter voltage is almost flat, and it is usually at VCE sat, and that is why we say the BJT does not respond to the base current variation when it is in the saturation region. Now, we will turn our discussion into the mathematical aspects. The equations relating the current is IE equals IC plus IB. The base current is effectively the input current and the collector current is the output current. The ratio of collector current IC to the base current IB is known as the current gain beta and is written as IB equals HFE equals IC divided by IB. The collector current has two components, one due to the base current and other one is the leakage current of the collector to base junction, and is given by IC equals beta IB plus ICEO, where ICEO is the collector to emitter leakage current with base open circuit and can be considered negligible compared to the first component in the RHS, which is beta IB. From equation 1 and equation 3, we will substitute equation 3 into equation 1 here, which will be IE equals, instead of writing IC, I will write beta IB plus ICEO. Then we also have beta IB here. So it will be IB into 1 plus beta plus ICEO. Now, since we already have stated the value of ICEO is considerably smaller and negligible compared to the beta IB, it will definitely be further negligible compared to IB into 1 plus beta. Therefore, neglecting ICEO, I will write the equation for IE as IB into 1 plus beta. Now, IB and IC are related as IC is equals to beta IB. Therefore, substituting that equation here, I can write the emitter current as approximately equal to IC into 1 plus 1 by beta. By simple multiplication here, I will get a simplified version of the equation as IC into beta plus 1 divided by beta. The collector current can further be expressed in terms of the emitter current as IC is approximately equal to alpha IE, where the constant alpha is related to beta by alpha equals beta divided by beta plus 1, or beta equals alpha divided by 1 minus alpha. We will now continue to discuss the transistor as a switch. Consider the circuit shown here where the transistor is operated as a switch. Let us apply the KVL to the base to emitter loop to derive an expression for the base current here. We will get IB equals VB minus VBE divided by RB. Now, coming to the collector to emitter loop, we once again apply the KVL to get the collector to emitter voltage, and is given by VC, which is also equals to VCE, equals to VCC minus IC into RC. And now we know that IC is equals to beta IB. Therefore, this can be written as VCC minus beta IB into RC. The expression for IB is taken from equation 10 and substituted in place of IB here to get VC equals VCC minus beta RC divided by RB into VB minus VPE. So this will be our first expression for the collector to emitter voltage. We now go back to the circuit to note that the collector to emitter voltage is also given by collector to base voltage plus the base to emitter voltage. Now let us write down that as an equation here. So collector to emitter voltage equals collector to base voltage plus base to emitter voltage. Rewriting this equation, I will get collector to base voltage equals collector to emitter voltage minus base to emitter voltage. This is a very important equation. Equation 14 here indicates that as long as the collector to emitter voltage is greater than or equal to the base to emitter voltage, the collector to base junction will be reverse biased and the transistor will be in the active region. The maximum collector current in the active region, which can be obtained by setting the collector to base junction or base voltage to 0, which will give us collector to emitter voltage equals base to emitter voltage, as ICM, maximum collector current, equals VCC minus VCE divided by RC. This can be obtained by simply applying KVL to the collector lobe. Now since when VCB equals 0, VCE becomes equal to that of VBE, I will modify this expression and replacing VCE by VBE. And the corresponding value of the base current, because IC and IB are related by beta, can be given as IBM equals ICM divided by beta. If the base current is increased above IBM, then the base to emitter voltage increases and the collector current will increase and the collector to emitter voltage will fall below VBE. Now coming back to this, now when the collector to emitter voltage becomes less than VBE, the transistor goes into saturation. The transistor saturation may be defined as the point above which any increase in the base current does not increase the collector current significantly. In the saturation region, the collector current remains almost constant. If the collector to emitter saturation voltage is represented by VCE sat, then the collector saturation current is given by ICS equals VCC minus VCE sat divided by RC, and the corresponding value of the base current is IBS equals ICS divided by beta. Further, the circuit is designed normally so that the base current is higher than the base saturation current. This ratio of base current to the base saturation current is called the overdrive factor, denoted by ODF, and is given by base to base saturation current. And the ratio of collector saturation current to the base current is called the forced beta and is represented by beta subscript F, and it is equal to ICS divided by IB. Lastly, the total power loss in the two junctions of the BJT is given by PT equals VBE into IB plus VCE into IC. A high value of the overdrive factor will not reduce the collector to emitter voltage significantly. However, the value of base to emitter voltage will increase due to increased base current, resulting in increased power loss in the base to emitter junction. Right. So that was about the steady state characteristics of the BJT. Thank you.